Welcome to Chapter 4, Nomenclature. Nomenclature is the system chemists use to name compounds and translate between the chemical name and the chemical formula. In this chapter, we are going to begin with the binary compounds, which contain only two elements. We will separate those compounds into three types based on whether they contain a metal and whether that metal can only form one charge. We will then extend the naming rules to compounds containing polyatomic ions. After that, we will learn how acids are named, including different rules for acids that contain oxygen and acids that do not. And then finally, we will reverse the process and write a chemical formula from a compound's name. This chapter requires very careful attention to patterns, charges, prefixes, and endings. The goal is not that we're going to memorize the individual names, but we want to recognize what naming system applies to something, and then we follow that system consistently. 4.1 objective is focusing on naming the binary compounds. We'll have the three objectives. First, we will learn to name the binary compounds from a metal and a nonmetal. These are ionic compounds, and the charge behavior of the metal determines whether the compound is classified as type 1 or type 2. Secondly, we will learn to name the binary compounds containing only nonmetals. Those are the type 3 compounds, and we'll use prefixes to show the number of atoms present. Thirdly, we will summarize the naming process for all three types of binary compounds. By the end of this section, you should be able to inspect a formula, decide which of the types of compounds it represents, and then apply the correct set of naming rules without mixing the systems together. And yes, it's going to be fun. Naming compounds that contain metals and nonmetals. Binary ionic compounds contain a positive cation and a negative anion. Cats are positive, onions are negative, and it's close enough to the word onion. When a compound contains a metal and a nonmetal, our first job is to determine what kind of metal is present. In a type 1 compound, the metal forms only one common cation. Sodium always forms Na+, cesium always forms Cs+, calcium always forms Ca plus 2, and aluminum always forms plus 3. And aluminum is one that depends on which book or what version we're looking at. But anyway, because each of these metals only has one expected charge, the charge does not need to be stated in the compound's name. In a type 2 compound, the metal can form more than two cations, so it can have different charges. Chromium may be Cr plus 2 or Cr plus 3, and believe it or not, maybe it could even be Cr plus 1. Copper may form Cu plus or Cu plus 2, but because the metal's name alone doesn't tell us the ion charge, type 2 must include additional information about that charge. So we'll see that here soon. All right, on this table, we've got a list of simple cations and anions used in binary ionic compounds. On the cation side, notice that hydrogen, lithium, sodium, potassium, and cesium form +1 ions. They're all in group 1. Beryllium, magnesium, calcium, and barium form +2 ions. They're in group 2. And now you might be thinking, aluminum, group 3. Calm your horses. But it also forms +3 ions, and silver is a +1. Silver is a special case, and we'll talk about that one in a little bit. These are all type 1 cations, and they keep the elemental name when they are named. On the anion side, the nonmetal name changes to "ide" ending, IDE. Hydrogen becomes hydride, fluorine becomes fluoride, chlorine becomes chloride, bromine becomes bromide, and so on. One of the ones that people sometimes get tripped up on is oxygen becomes oxide, so don't get tripped up on that. The colored roots on the table emphasize the part of the element name that it was before we added the IDE, so you can see some of them keep more than others did. The ion names are the building blocks that we use when we combine to make ionic compounds. All right, here are our rules for type 1 ionic compounds. First, the cation is always named first, and the anion is always named second. The second rule, a simple cation formed from a single atom keeps the name of that element. for an example, Na plus is called sodium. Third, a simple anion is named by taking the root of the element name and adding IDE ending. Chlorine becomes chloride. Fourth, we combine the two ions and produce the compound name. We do not use prefixes to indicate the subscripts in a type 1 ionic compound, and we do not include a Roman numeral because the metal only has one common charge. The formula tells us the ratio needed for an electrically neutral, but the name is simply the cation followed by the anion name. So if I was to put sodium and chloride together, I'd be getting table salt, which is sodium chloride. All right, so just to show that in another way, to reiterate, any binary compound has a metal and nonmetal. The metal is named first. The nonmetal is named second using the root of the element followed by IDE. The example we've got right here is NaI, sodium and iodine, but because it is an anion, it's iodide, so that's sodium iodide. And then for the next one, you'll notice we don't do anything special just because they have a 2 plus and a 2 minus. Their name is still calcium oxide, from calcium as a cation and oxygen as an anion, so oxide. We do not say any kind of mono because there's one of them. We only say what they are, and if it's a non-metal, we add IDE to the end. Exercise time. Let's name the following compounds. We have KCl, we have MgBr2, and we have BaO. Let's try to name these. I'm going to give you a little secret. They're all going to be type 1. And now I'm going to pause it because Wayground will make you do it. All right, so let's start with this first one, KCl. We know K is potassium, and we know Cl is chlorine. Now, since it's a type 1, I know that I have to take the anion and add IDE, which makes that potassium chloride. We did it. All right, magnesium is a +2. Bromide is a -1, so there are two of them. Do I need to know that for this? No. I just need to know that it's magnesium and bromine, but bromine becomes bromide, so it becomes magnesium bromide. The last one is barium, which is a +2 cation, and oxygen, which is a 2 minus anion. I put them together and I get barium oxide. We did it! Because they all have common charges, we don't have any kind of Roman numeral. And because they're not all nonmetals, they don't have just prefixes with them. All right, naming type 2 is a little bit more difficult because the metal that forms the cation can have multiple charges. So gold and chlorine go together. Which one do I make? Do I make a gold and a single chlorine, or do I make a gold and 3 chlorines? That depends on which form of gold's cation is present. We can't call both substances gold chloride because they will react slightly differently or have slightly different properties. Even though most of that has to do with the electrons present, this does change the overall structure, so the 3D shape can be different. We need to use a Roman numeral now to specify the charge of that gold when we are in the formula making process. All right, so you'll see on this table we have multiple forms of different cations that are possible. We used to, instead of doing the Roman numeral version, you used to have to know how to spell the different forms, which, as you guys can probably guess, was not the easiest thing to do. So we started using the Roman numeral version instead, and it is a lot less ambiguous or a lot less ways of messing it up, because something like ferric and ferrous or cupric and cuprous, they look very similar. You probably wouldn't know right off the bat looking at them, but you know a Roman numeral 2 will be a +2. So we will use the systematic Roman numeral system. When we have a type 2 compound, the charge is not guessed from the metal. We have to know the charge because we're going to base it off of the anion connected to it, knowing that it has to be electrically neutral or equal 0. So if I have lead 2 and I have an oxygen, to get lead 2 oxide, I would just have one oxygen because oxygen is 2 minus. We'll talk about that more as we see them. Exercise time though, so let's see if you can do this one. Name the following compounds. We have CuBr, we have FeS, and we have PbO2. Oh no, spoilers. Did I tell you one? I don't know. We're about to find out because it's going to make you do it on Wayground. All right, welcome back. The first one, of course, is copper bromide, but what form of copper? Well, copper can have multiple charges. We know it can have a +1 or a +2. So what does it have in this version? Well, I've got bromide, which we know is in group 17, which must mean it has a -1, which would tell us that that copper is copper 1 bromide. And one of the very few that doesn't always have to have a Roman numeral in other examples. A lot of times, if it's a charge of 1, it doesn't always get shown. But for this class, we're going to make sure we still show that it's copper 1 bromide. The next one, iron sulfide. But which sulfide, which iron would it be? Well, that all depends on our sulfide's charge. So if you look on your periodic table, you'll see that sulfide is in the group 16, which would mean it is a -2 charge. And if I only have one iron, then that iron would have to be what to equal 0 plus -2? That's right, it'd have to be 2. So that's iron 2 sulfide. The last one, kind of already gave away in the last slide. If I have to have a charge equal to what oxygen's negative charge is, remember oxygen is -2 and I have 2 of them, bringing us to -4, the lead would have to be 4. So we have lead 4 oxide. Remember our Indians, we don't lose on any of the anions. They are simply helping us figure out the charge of the cation. All right, so our type 3 compounds are going to be very different from everything we just did. The naming system is not ionic at all. It's actually covalent. We'll talk about that second semester. So our first thing we're going to do is we're going to get the name of the first element, and then we're going to use the full element's name. The second is we're going to name the second element as if it were an anion. So we're going to use that IDE root. And third, we're going to use the prefixes to indicate the number of atoms of each of the elements present in the formula. Fourth, the prefix mono is never used for the first element. For example, CO is carbon monoxide, not monocarbon monoxide. The prefix vowels may also be adjusted to make pronunciation smoother, as in monoxide rather than monooxide. Unlike ionic compounds, these are molecular compounds, and they do not use subscripts to determine the prefixes of the name. You'll see what that means in 1 second. Here is our list or table. It gives the prefixes we use for type 3 compounds. So we start with mono for 1, di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, hepta for 7, and octa for 8. Exercise. Name the following compounds. CO2, SF6, N2O4. I'll give you a second so you can try to answer them yourself. Welcome back. For the first one, we will name the first element in its elemental form, which is carbon. We did it. We know we're also going to add IDE to the second element's name, so we will call it carbon oxide. The special thing about these compounds, if they are the type 3, is we need to add our prefixes. We never say mono for our first element, so it's going to be carbon. We don't touch that anymore. But we do have 2 oxygens. And if we think back to our previous list, we know 2 has the root di. So that becomes carbon dioxide. You know it, you exhale it. Next one, we're going to start again. Since there's only 1 sulfur, it is going to get the name sulfur. The next part is a little bit harder unless you remember your shapes from geometry. We know it's fluoride because that's fluorine, and then we change the ending to IDE, but we have 6 of them. 6 sides. Oh, hex. So we call that sulfur hexafluoride. And here's the tricky one. They're going to try to trick you, but we won't let them trick us. Now we're going to write the name nitrogen. All right, but what's different about this one is that we have two of them. And since it's not mono, we're going to have to give a prefix to this nitrogen. It's going to be dinitrogen. And then we look over and we see we have oxygen again, so we know that's going to be an oxide. But we've got four of them. So what is a prefix for that? Oh, that's right. It's not quad, it's tetra. So to change the letters a little bit, we get dinitrogen tetroxide. There's not an A and an O together. I know. But that's the name. Great job. All right. Here's a great flowchart that you should try to make sure you understand before we do any kind of assessment on this material. We're going to begin by confirming, of course, that the compound is binary. If no, I don't know what you do. It's not a binary compound. There's no option. So we're going to say, yes, it is a binary compound. Then we're going to go and look to see if there's a metal. Because if there's no metal present, then of course that's a type 3. That's when we're going to use prefixes, like we just did. If there is a metal present, yes, is that metal one that is likely a transition metal? If yes, then that's a type 2 where we're going to need our Roman numerals. And if it's not, then that's a type 1 and we'll use the element name for a cation. Very simple and straightforward, and none of us are going to mess this up even once. Right? Exercise. You show me. Which of the following compounds is named incorrectly? That must mean some of them are named correctly. I'll give you a moment to think. All right, let's go down the list. K3N, let's see. Potassium, that's going to be +1 charge, right? And nitrogen is a -3 charge. Even if we didn't know that, we could look at the periodic table. We would know that. So doesn't seem like it'd be anything special to me. That would be correct. That's a type 1. Next one, we have titanium 2 oxide. Let me think. Well, oxygen is -2, and I've got two of them, so I would say -4 total, but the formula tells me titanium 2 oxide. That seems suspicious, so we'll mark that on our suspicion meter. We'll move on. All right, next one we've got tin bromide, and it's given us 4 as our charge on the tin, and that tracks because bromine is a -1 because it's in group 17, and I have 4 of them, so -4 to get to 0. I would need a +4 on the tin. That looks correct. Phosphorus pentabromide. Phosphorus and bromide, both nonmetals, so I would need the penta on the bromide. That tracks for me. I agree. And there are 5, and that's the root penta, and there's nothing weird with the phosphorus. They didn't put mono on there, so we know that's good. And then E, we have calcium sulfide, calcium metal in group 2, and sulfide is a nonmetal in group 16. So that all tracks. I think that is correct. So I think we're going to go back to B and say, that's the guy. It's wrong. We would need a charge of 4, which would mean the name itself is good. The Roman numeral provided would need to be an IV for 4. If you don't know your Roman numerals, you really only need to know up to 4 for this class. So make sure you know IV is 4. Congratulations, you did it. All right, if you weren't thinking that was hard enough, what if instead of having um, a single atom as our naming piece, we're going to use a group of atoms called a polyatomic ion? If that's you, great. For the rest of us, pay attention. We're going to extend in 4.2 our nomenclature talks to more complex compounds. And of course, those are the ones that we're going to see more in this class. So make sure we know this, and we'll be adding on to this all year with different polyatomic ions. First, we're going to need to learn the names of the common polyatomic ions. You're going to have to memorize some of these just by the amount of times we use them. Second, we're going to use the ions to name ionic compounds, just like we did in the last section. Third, we will examine how the composition of and endings of an anion determine the name of an acid. That one will come up a lot more throughout the semester too. And fourth, we will learn several common acids. And then finally, we're going to go backwards just like we did before and name the chemical formula based off of the compound's name and vice versa. This section combines all of the charge balancing ideas from the ionic compounds with the new ion names and acid endings. Because a polyatomic ion behaves as one charged unit, it is important to recognize the entire group rather than treating each element individually in the group separately. All right, you ready? I am. Naming compounds that contain polyatomic ions. Believe it or not, poly means many. So that means that these are ions that have multiple different atoms bonded together. Each entire group carries a net charge, so we'll need to know the charge, and it has a special name that we have to learn. The table includes a lot of different ones that we'll need to know. We'll go through these as they pop up. Some of them we'll use a lot more, like hydroxide, which is OH minus. The nitrate and nitrite we'll use fairly frequently. Uh, some stuff like chromate we probably won't use as much, uh, or dihydrogen phosphate, but we'll need to know certain ones of these that we'll talk about more in class. Uh, when these groups appear in a compound, we need to keep the polyatomic ion together as a single named unit. So it is replacing what we would think of as an atom in that case. The internal subscripts are part of the ion and we can't change them. So if I have a nitrite, I have to have NO2, and sometimes that's in parentheses, sometimes it's not, but we keep it as a unit. I can't change any of those pieces or else I change what it means to be a nitrite. We'll see those more as we continue. Ionic compounds contain polyatomic ions. Follow the rules that we already learned for ionic compounds. The named cation goes first and the ion goes second. The anion goes second using the names of the polyatomic ion. So our example is ammonium acetate. The formula contains NH4 plus, which is the ammonium ion, and C2H3O2 minus, which is the acetate ion. The name, therefore, is ammonium acetate. We do not change the acetate to "ide" ending because the acetate already has its own ending as a polyatomic ion name. We also do not use prefixes to describe the number of atoms inside either ion. Think of polyatomic ions as a package that remain together. When more than one polyatomic ion is needed for a formula, we use parentheses around the entire ion before adding the subscript. We'll see what that means in a second. Exercise time. Name them. K2CO3, MgOH2, and NH4 3PO4. Now, since I don't expect any of you to have these memorized quite yet, we'll start with that first one. K2, nothing special there. That's just potassium. CO3 is a carbonate ion, and that is a 2 minus, so it does cancel out correctly. So its name, since it's with a carbonate, we don't change the ending. Potassium gets nothing. It's just potassium carbonate. The next one of the ones you will need to be able to recognize very quickly is OH, which is hydroxide. And since we don't have to do anything with the metal, it's just magnesium hydroxide. The next one has two polyatomic ions, which will come up, but less frequently in this class than in college chemistry. But you do need to know that it is possible. This is ammonium, which is the NH4, which is, we'll talk about later. We don't use it that much, but it is one of our only polyatomic cations. And then the PO4 is phosphate, so we just slam those names together, and they gave us ammonium phosphate. All right, and then naming acids. I'm actually not super upset if you don't know how to do this, so don't be like, well, there's another one they're adding on. I want you to generally understand these. I want you to more memorize these than I would anything else in the class because learning the names for acids, while not difficult, if the anion doesn't contain oxygen, we'll just change the prefix to hydro and add ic. One of the most important acids we'll use in this class is hydrochloric acid, which is just HCl. So since it doesn't have oxygen in the anion, it's just hydro instead of hydrogen, and then chloric from chlorine, adding the IC, and then we say the word acid. You need to know hydrochloric acid. If you want to learn the other ones like hydrosulfuric acid, be my guest. Here's a couple of the generic acid or common acids that don't contain oxygen. HF is one of the most seriously dangerous acids you could work with, so we won't be. And then the other ones you can see just have that ending. The special one, of course, is the HCN. That's cyanide. It's a polyatomic ion, so hydrocyanic acid. But again, we won't be messing with those acids, so don't worry about it too much. Naming acids that contain oxygen is way more difficult, which is why I won't be making you do that. They don't get the hydro prefix. Instead, the ending of the anion determines the ending of the name of the acid. If the anion name changes in ate, the ate changes to ic in the acid. So sulfate becomes sulfuric acid. Phosphate becomes phosphoric acid, and acetate becomes acetic acid. If the anion name ends in ite, it changes to os in the acid. So sulfite becomes sulfurous acid, and nitrite becomes nitrous acid. The central element or anion root remains recognizable, so we still know it, but the ending changes. A useful way to remember the pattern is ate becomes ic, while ite becomes us. Always begin by identifying whether oxygen is present in the anion because it determines whether hydro rule is used or if oxygen containing acid rule is used. Again, not super important that you memorize this one as long as you remember the other naming structures. We come into acids infrequently, so I will help you remember the name. This is more just to start to learn the process of how they're different. If they have oxygen, they're going to have ic and os still, but they're going to vary depending on if it was the anion or not. And here's the list of those. We will use different nitric acids throughout the year and sulfuric acids. Acetic acid you probably have used in your normal life because that is vinegar. And then here's another flowchart. Again, not super crazy. If you were to learn anything from the naming acids part, I would try to learn this flowchart. It tells you the direction to change all of your stuff and whether or not to use hydro or not. And it all depends on, do I have oxygen in my anion? Good work, and we'll continue on with the next part. Exercise, name the following acids. Oh boy, NO3. That's a nitrate ion, so I'll give you a little hint there. What do you think we could change nitrate into? It contains oxygen, so we won't use hydro. That's right. That'd be nitric acid. If you've ever had sour Skittles or sour, what are the little guys called? Wow, I'm blanking right now. What are the sour guys called? I refuse to pause the recording, and you're just gonna have to sit with me while I remember. Sour Patch Kids. They have a little bit of nitric acid on the outside. It's common in a lot of fruits. The next one, not a tangent, I promise, is hydrogen and bromine. But since it's an acid, it does not contain oxygen. We are going to have to use the hydro in the prefix, so it becomes hydrobromic acid. And then the next one, cool, right? It's got oxygen. I know. Remove the hydro. I know that it is a polyatomic ion because there's three things there, and that shouldn't happen otherwise. So if I look at PO4, that's phosphoric now instead of phosphate ion, and that changes to phosphoric acid. We did it. We named them all. We are the best. All right, so now what if I told you, and I am telling you, you're going to have to be able to work backwards from some of these on tests and quizzes to know how you got there. On something like sodium hydroxide, you need to know hydroxide off the top of your noggin is OH minus. If you can do that, the other part is easy to figure out. If you only know the sodium part, you probably won't be able to figure out the rest of it other than knowing what hydroxide is. The next one, potassium carbonate. If you don't know the charge of a carbonate is 2 minus, then you have no way of figuring out how many potassium you need. Sulfuric acid would require you to know that your sulfur-containing sulfate ion becomes sulfuric acid because it is a 2 minus, and I need 2 hydrogens with it to knock that down to a 0. And dinitrogen pentoxide, I'd only know that if I know the roots and I know both nitrogen and oxygen. And then your favorite one, cobalt-3 nitrate, you need to know that a nitrate is a -1 charge. And if I have 3 nitrates, remember I put the parenthesis on the outside of its polyatomic ion, then my cobalt could just be a +3. Yes, we need to know how to do a lot of things in this unit, and I believe in all of you. Let's try it right now. What is the formula for each of the following compounds? Barium chloride, copper 1 nitrate, iron 3 sulfate, and phosphorus pentabromide. I'll give you a second to figure this out, or I'll put it as a matching thing on Wayground. Which did I do? I don't know. All right, let's start with barium chloride. Barium is a +2 cation, and chloride is a -1 anion. So let me think. Is 1 and 2. Does that do 0? No. All right, then I need to do a little bit of barium chloride. Nitrate, as we remember, because I just said it in the last slide, is a -1 anion. That's NO3. And if it's copper 1, what do you think the subscript should be on copper? If you said 1, you're wrong. It's nothing because it's 1. Iron 3 sulfate should tell you a little secret. Sulfate, believe it or not, is going to have to work with iron 3. So does that tell me directly how many iron I need? No. And that's where it can get a little bit confusing. So what am I supposed to do? That's a great question. Iron 3 sulfate contains Fe3+, which is from the 3, and the sulfate anion is a 2 minus. So the least common charge that we could have together from like least common denominator kind of thing, LCD, between a +3 and a 2 minus would be 6. So I would need to do a little bit of math and figure out to get my 6 from 3, I need 2 iron and I need 3 sulfates altogether. And then the last one should be easy since we don't see a prefix on our phosphorus, and we know that phosphorus and bromine are both, say it with me everyone, non-metals. I hope everyone said it, or else I'm going to look dumb. Then we know that this is all I have to do. And you've done it. Congratulations, everyone. You've made it through one of the hardest sections of chemistry, and I'm not even joking about that. There's a lot of rules in here. Go and congratulate yourself and get ready to discuss this in class. See you next time.